thank you everybody for coming. Today I'm going to talk about some things that we can do with ZKPs. And like some of the background for why I think that this is important is that like at the moment there's a lot of applications on Ethereum, but those applications appeal to like a relatively small set of the like global population. A lot of people are not really interested in NFTs and DeFi, and like I think with good reason. I mean, it's compelling for a bunch of people, but for a bunch of other people it's not. And like I see these arguments happening sometimes, and I think that like instead of trying to argue with people about like why crypto is better, we should try and find use cases that are compelling to them. So today I'm going to talk about like some of those potential use cases and show you some examples of some things that are kind of out there and we can use right now. Cool. So before I do that, I'm going to need to talk about a couple of different primitives, and like my idea here is that I want to keep this talk high level, so I want to apologize to the cryptography experts who are here today. We're not going to get into like deep cryptography. Instead, we're going to black box out these components and try to use them to build interesting things. So, yeah. So we're going to box them out, and like when I started building things with Ethereum, I didn't learn how ecdsa signature scheme worked. I didn't learn about Merkle Tree. I sort of black boxed those things out, and I said, oh, here's a cryptocurrency. I know a signature, only I can make a signature and other people can verify it. I know that data that I store in a smart contract is going to be available, and that's all that I needed to know. I knew what it did, but I didn't know like all the inputs, and I didn't know exactly how it did it. And this was a very like good way for me to be able to learn and build things without having to spend like a year just studying and learning about all these different things. That said, like it seems like there's two paths here. Like one path is to like go really, really deep and learn like lots of crypto, and the other path is to sort of black box things out and make things with them, with crypto. And like both are definitely valid paths, but I'm going to focus on the path of like black boxing things out and trying to build things and use things, because I think that that's like a fun way to get started, especially if you're like more of a beginner in the cryptography side. Okay. So yeah, the first thing I need to talk about is a hash function. So basically what a hash function is, it takes this like ordered data here on the left-hand side, it performs some algorithm, and it mixes up the data so much that on the other side, you're not able to find out what the original data was. So like it has like 3 guarantees. The first guarantee is that you can't find like 2 sets of data that leads to different data on the other side, or that leads to the same information on the other side. So this is called collision resistance. The second is that like you can't go backwards. That means that like with the data on the outside, on the right-hand side, you're not able to go back to the left-hand side. And the third thing is, what was the third thing? Yes, the third thing is that the data on the right-hand side is smaller than the data on the left-hand side. Okay, so this is what a hash function is, and I'm going to talk about hash function today, but like the best way to think about it, it's just like a blender. It's like you put the data into the blender, you run the blender, it gets all messed up and mixed up so that you're never able to go back to the original data that was put inside. And it also takes up less space because you blend it up, it gets smaller. Okay, so the next thing that we need to talk about is a Merkle tree. And a Merkle tree is a way of using these hash functions to sort of create a commitment to a large amount of data. In our use cases, we're going to have this big set of users, and we're going to want to compress that set into like the smallest possible representation. So to do this, we use what's called a Merkle tree, and the advantage of using a Merkle tree, rather than just putting everything into our blender and running our blender, is that it's easy to go back. It's not easy to go back, but it's easy to show, oh, this piece of data was in the original set. It's easy, okay, so here's a Merkle tree and here's how it works. So at the bottom layer, we have our data. And then our data is 512 bits, for example. Let's take that, and then the first thing we do is we hash our 512 bits so that we get an output that's 256 bits. And that's our first layer. And then we take our 512 bits from the second layer, because we have 256 bits on the left-hand side and 256 bits on the right-hand side, and we hash that together again, and we get another 256 bits. Then we take 256 bits and 256 bits, hash it together, and we get our final, what we call our Merkle root. This is called a Merkle tree, and the top node is called the Merkle root, which is like a a succinct representation of all the data that we have on the bottom layer. And the advantage of this is that like a user who knows the value of like the bottom layer is able to provide a proof, not a zero knowledge proof, but like a just regular proof that they know that data. So we're going to use that a little bit later. The third thing that we need to introduce is a zero knowledge proof. So a zero knowledge proof is basically a way for someone to make a proof about public and private information. That normally when I want to prove something to someone, I show them all of the data. And they say, oh, they run some algorithm and verify that it's correct, and then we're done. But like this is limited because I need to show them all the data. So zero knowledge proofs allow us to hide some of the data. And that's the advantage here. So you can see this example I have here. So this is basically a zero knowledge proof that proves that I know the product of A and B. Oh no, sorry. This is a zero knowledge proof that proves that I know an A, a public A, that multiplied by a private B equals C. Okay? So we have our public input A, our private input B, our check, which is A multiplied by B equals C, and our output is C. So this is what the prover sees. Now, an important thing to remember about ZKPs is that the prover knows all of the data. Everything that goes in, they know it. And this is like one limitation that we need to consider. Anyway, this is what our prover sees. Let's look at what the verifier sees. So the zero knowledge proof kind of blacks out some of the inputs to the circuit. So let's notice a couple of things. First of all, they know the public input and output. This is important because we need to be able to reveal some information to them. And this is how we do it, by having public inputs and outputs. The second thing to notice is that they know the algorithm that's being checked, that they're aware of what's happening, what checks we're performing. And this is also important, because if they didn't know what checks we were performing, we wouldn't be able to, if they didn't know what checks we were performing, we wouldn't be able to, they wouldn't be able to trust the actual proof that we're giving them. Okay, so this is what a zero knowledge proof is. We abstracted away all the complexity of the math, and this is a tool that we have. So let's use that tool to see how some things that exist in the world work. So the first thing is Zcash. So Zcash is a cryptocurrency that uses zero knowledge proofs to allow users to send private transactions. And the way that it works is that, let's look at the ZKP that they use. So this is like our original example. This is what the prover sees. This is what the verifier sees. Let's talk about what the prover sees. So the prover sees everything. The prover says that for some Merkle root, this green block in the input, I know a Merkle proof, a public key, a private key, and a nullifier such that the public key and a Merkle proof results in the Merkle root. This Merkle proof is not a ZKP, it's just a certain set of hashes that they perform. So first of all, we check that the membership is correct, and then we need to check that the public key, that they own this leaf. So this is basically, we convert their private key to a public key. And the final thing that we do is reveal a nullifier. And the nullifier is important because it prevents double spends. So let's look at what the verifier sees. So the verifier sees the Merkle root, it sees that the checks that are performed, and it sees a nullifier. So the Merkle root is basically the list of all of the users who are able to send a transaction. The checks are the membership check. They see that, but they don't see any details about the membership check. Because if they did, they would be able to see, oh, which user it was. They'd be able to see their public key, they'd be able to see their Merkle root and the Merkle proof. They'd be able to identify exactly which user it is. So we have to hide this information. The second thing we need to hide is the private key. Because if they saw the private key and the nullifier, they would be able to make a proof for that same leaf. And number one, we would lose privacy because they would be able to calculate the public key and they would be able to find the public key in the Merkle tree. The second thing that would happen is that they would be able to steal this money. They would be able to make a transaction to spend it somewhere else. So we have to hide both of those things. And then we reveal the nullifier. And the nullifier is super important because it prevents double spends. So let's talk a little bit about the verifier algorithm. So the verifier algorithm, when the verifier gets this proof, first of all, it checks that the ZKP is correct. Then it checks that the Merkle root is a correct Merkle root, that it's a correct list of users that are able to send transactions. Once it confirms that check, the second thing that it does is it checks the nullifier has not already been used, because we have a 1 nullifier per user limitation here. That's enforced by this hash. Once you spend a nullifier, you're not able to spend another coin. And the verifier enforces this by storing a list of all the nullifiers. And if it sees the same nullifier twice, it will reject that proof. If there's a second proof with the same nullifier, it'll say, no, this is not valid, reject. Okay. Okay, so nullifiers here are important to prevent double spends. Cool. So let's talk about like some generalizations of this idea. So the first thing is semaphore. And semaphore kind of generalizes this protocol because in the previous example, you could only make 1 ZKP. As soon as you made 1 ZKP, your nullifier was revealed and you couldn't make another valid ZKP. If you did, the nullifier would be the same. So semaphore generalizes this and it allows us to reuse public keys. So this primitive allows us to make a bunch of interesting things. We can do like private voting, we can do anonymous social media, we can do a whole bunch of like interesting stuff with this, which I'll talk about a little bit more soon. So the next example I want to talk about is like another generalization and improvement on the idea of Zcash. Maybe it's not an improvement, it's more like a specialization. And this is called rate limit nullifier. So this is a special kind of nullifier that we use to limit the rate that messages can be sent. So semaphore lets you prove that you're part of a group, and RLN enforces a rate limit on that group. So like the idea is that we have an epoch. During this, an epoch can be like 1 hour, 1 minute, 1 second. During this epoch, you're able to send 1 message. If you send more than 1 message, your public key gets revealed and you get slashed. So how can we do this? The way that we do this is we use Shamir secret shares. And basically the idea of Shamir secret shares is that we have a private key, and we encode that as 1 point on our line. Then every time we make a proof, we reveal 1 point on this line. And the idea here is if you have 2 proofs on the line, if you have 2 points on the line, you're able to interpolate the rest of the line. You're able to find the whole line. Once you find the whole line, you're easily able to find the private key. Okay, so let's use this in our ZKP. So here's another ZKP. This is our prover's view. Our prover sees everything. So it's very similar to the Zcash ZKP that we talked about a minute ago. We have our Merkle root, we have our Merkle proof, our leaf, and our private key. We prove that the leaf is in the private key, and then we reveal a Shamir secret share of the private key. And the way that we do this is just A multiplied by the message plus the private key equals the output. Okay, so here's what the verifier sees. So the verifier will see the Merkle root, the membership. It won't see the details about like which leaf it is, but it will see the message that was signed, and it'll also get the share will also be revealed. And so the share is kind of stored every time the peer-to-peer, every time the verifier receives RLN proof, they will basically say, every time they receive a proof, they'll basically get the share, and then they'll check to try and recover the private key of that leaf with all the other shares that they've received. And if they can do that, they'll generate the user's private key, and they'll reject the proof. They'll also share that private key with everybody, all the other verifiers in the system, and they'll say, this user sent me an invalid proof, or this user sent me more than the allowed number of messages. They're no longer allowed to send messages. And all the other verifiers will accept this and continue with their day. Okay, so let's talk about some applications of this. So this is Skitter. Skitter is a social media experiment built by this anonymous person called Tsukino. And basically the idea is that it uses a semaphore to make proofs that you're part of a group. And every time you make a post on this social media application, your posts are not connected to your identity. Your posts are connected to like one of a bunch of groups. Yeah, so they have this really fun social media experience. It's very fun to think about like what are the implications of this and like how will this be used in like social media in general. So let's have a look at some stuff. So here's a post. This is a post on Skitter So this is from, there's a couple of groups on Skitter right now. They're mostly about Twitter followers. We have like a centralized bridge to export this credential. And the idea is that it's like a way for us to experiment. It's a nice way for us to build these like groups. But like some of the negatives are that like it's centralized and like the reputation is not really very meaningful. But it's nice to use an experiment, and it can lead to some fun kind of interactions. So yeah, so this is a post from someone with more than 500 Twitter followers who was talking about, oh, they really like the new feature on the site, the dark mode. And this is another member of that group who's saying that, oh, the feature is a little bit tricky to use sometimes. So like, what do we know here? Well, we know that like this came from like more people with more than 500 Twitter followers. Okay, so let's talk about the anonymity set. So the anonymity set is a set of people who could have made a proof. So when we talk about ZKPs, we also always need to be careful about the anonymity set. We want to maximize the anonymity set, but we also want to maintain some signal. We want users to be able to, if we have like a completely anonymous thing where posts are not connected to anyone in any way, it can be like a very low quality experience for people. That like it's just possible for people to send thousands and millions of messages, and it's hard to like use that to, yeah, it's hard to use that as a way. That can lead to some difficult social media experiences. So let's talk about the anonymity set. So we have like 3 groups. The gold group, which is I think more than 2,000 Twitter followers, the silver group, which is like between 500 and 2,000, and the bronze group, which is more than 500. So these are different groups, but at the moment they're very small. There's like 5, 3, and 6. So the anonymity set is currently starting to grow, but it's still so small that it's like not. It's more like growing than it's ready for people to use and be confident about their privacy when they're making posts. So it would also be nice to add some decentralized groups here, like POAP or BrightID. Like the more groups that we add can lead to more interesting discussions. And like we can also have like custom groups and interesting things like that. That might also be fun. Cool. There's also user accounts. So you can make a post here as like a user and there's no ZKP involved. So you're able to have conversations with like these anonymous groups, and you're able to like discuss with them and kind of see what they're, yeah, you're able to talk with them and have discussions and interactions. Another feature that it has is instant messages. So we use ORLN to make ZKP. We use ORLN to limit the number of messages any user can send, and this allows us to have like private direct messages. So you're able to chat, users are able to chat to users, groups are able to chat to users, and groups to groups is coming soon, it's not here yet. So this is a conversation I had with with a member of the 7,000 Twitter followers group, but they haven't got back to me yet, so I don't have any advice to share about getting more followers on Twitter. So hopefully soon. Yeah, so you can DM me on Skitter if you like. I'm there. We can start to have some chats. Yeah. We have. Yeah, there's a couple of other like interesting social media applications that I want to mention here as well. There's Hey Anon from 0xPark, which I'll talk about a little bit more in a second. There's people working on interesting groups like Seismo and Hey Anon. They also have some groups. And like one thing that we need to have is like a browser plugin so that we're able to use the same public keys, private keys with different applications. Just like MetaMask, you don't want to make signatures on Uniswap and SushiSwap and share your private key with the actual application. Because if they steal your private key, they can just take all your money or take all your reputation and just go and do whatever they want with it. So that's not good. So we need to be able to hide the private keys of the users. And that's why a browser plugin is really important. Cool. Okay, so there's one more application I wanted to mention for the hackathon purposes, because it seems like there's some fun things that we can do here. Yeah, so here's a link. And basically what this is it's a starter project that allows you to verify ecdsa signatures inside a ZKP. And why is this interesting? Well, you noticed earlier that our anonymity set was very small for the Twitter bridges. And this is because we have to have a public way for people to sign up. And like when we have a public way for people to sign up, you're able to see who signed up and who didn't. You don't know who performs what messages, but you do know the set of people who are inside the group who could have done it. So if we use ecdsa signature verification inside a ZKP, it becomes easier. Because then the anonymity set can be everyone who is in the participating set. So let me give you an example to try and make this a little bit more clear. So let's say that we want to make a group of every Ethereum user ever. What we do is we need to go to Ethereum, we download the list of accounts in the state, and we basically say that this is every valid Ethereum user ever. And what we do is we put them into a Merkle tree, and then we create our circuit. And our circuit is basically checking that the ecdsa signature is correct, and that they're part of the Merkle tree. So this can lead to a whole bunch of interesting applications, and one of them is Hey Anon, which I mentioned a minute ago. So Hey Anon is this it's a series of Twitter bots that will kind of copy and paste the ZKPs that they receive. And this is interesting, but one of the limitations is there's no nullifier. And when you have no nullifier, you're not able to have. When you have no nullifier, you're not able to. We could have a lot of problems with sock puppets, with people with the same account just pretending to be from different accounts. And this could lead to some problems. But we're working on ways to make the ecdsa nullifier generation better. And yeah, we're working on ways to generate a nullifier from ecdsa, and we're hoping that we'll be able to use that feature soon. Because yeah. Like, I'm really excited to have a whole bunch of different groups of like different kind of subsections of the Ethereum community able to like discuss and talk from that group. I think that would be really nice. We're able to do that already, but it involves us kind of like verifying on-chain the signature, and that limits the anonymity set. The benefit here is the anonymity set is bigger, and as soon as we have nullifiers, it's going to be really, really nice. Okay, another thing that we can do with this is we can use the ecdsa signature verification to compress the amount of signatures that you need to put on chain for optimistic rollups. Like y'all may have heard of the BLS wallet project, which is a project to compress BLS signatures into the smallest possible call data footprint. And like the reason for this is that call data is the only thing that matters anymore. Execution is basically free, so we want to minimize the call data as much as possible. So BLS wallet tries to do that, but we could also do that for ecdsa with a zero-knowledge proof. So this is a nice kind of scaling project that you could also work on. Okay, here's a couple of cool ideas. Do something cool with Semaphore. Reach out to the mentors. Jake is here in the blue t-shirt, and one sub is here also in the blue t-shirt at the back. Okay, so you can reach out to them, they'll be happy to help. One sub also wrote this library, so he's pretty knowledgeable about the ecdsa signature verification. Yeah, so other things that would be fun. It would be nice to add more groups to Skitter. At the moment, it's just like 3 Twitter follower groups and 1 like global user group. So it would be nice to add more users there or more groups there, just so different people are able to talk and like interact. It would be nice to make a version of Hey Anon that's like a message board or more like a message board. And it would also be nice to have like direct messages there too, just so you can have some private conversations as well. You can have a private conversation with someone who's part of that group without knowing like which person it is. And that might also be fun. Or another one is just go with your imagination, make another application that uses zero-knowledge proofs. I think there's a whole bunch of interesting things that we can do. And I also think that it's super important that we do it because we need to make applications that like are interesting for like a broader set of the global community. I think at the moment where our kind of focus is very narrow, and we need to broaden that focus in order to show people like why what we're doing is interesting. And that's really up to us, I think. If people don't get it, it's hard for me to blame them. I always think that, okay, well, let me try and show them something different, something that is maybe more compelling to them. So that's my talk. Thank you very much. If you're interested in joining to work with us, you can check out our website here or join our Discord. And yeah, thank you so much. Any questions?